Welcome to the INtersect, where DoD, industry, and academia meet. I'm Matthew Butkovic. I'm joined by my colleagues John and Jason this afternoon, and we'll be talking about quantum, advanced classical computing, and a number of topics related to this emerging field. Greetings, Jason and John. Thanks for joining us.
Thank you.
So there's quite a bit to unpack based on that introduction. But let's first start with introductions of your own. So, Jason, maybe if you could tell us a little bit about yourself and maybe a little about the path that brought you to these topics today.
Okay. Yeah, so I started off like my education and training in engineering, condensed matter physics. And then by the time I got to my PhD, which I did here at Carnegie Mellon, I started to work with high-performance classical computing, modeling, and simulation. And then that sort of started me on a path to more computer science type applications. But I had this quantum physics training in my background, waiting around. And now we're seeing all this funding and development in quantum computing. And it's kind of bringing those two threads in my past back together again.
Thank you. And John, how about yourself?
Sure. So I have a PhD in electrical engineering that I got from the University of Wisconsin. I studied theoretical and computational aspects of high-power microwave devices, which is a long way from what we're going to talk about today. So for my postdoctoral work, I went to Los Alamos National Laboratory. And after my postdoc was done, I took a job in the computational sciences division, where I worked on code implementations on supercomputers of models of high energy density physics. And so that went on for sort of over a decade. And as that went on, I became more and more interested in performance engineering and very low level details of advanced computing. 4 years ago or so, my wife and I decided we were going to try something new. And we came to Washington, D.C., which is where I am. And I worked for a contractor supporting the Department of Defense high-performance computing modernization program. So just 2 years ago, I joined the SCI, and the ETC is our group, the Emerging Technology Center, which has a large focus on AI and machine learning. And when I joined SCI, I had never implemented a neural network. And it's been a good couple of years coming up to speed on AI and ML and advanced computing aspects of AI and ML.
Hey, thanks, John. And thanks, Jason, for the overview. So I'm hearing that there's really an interesting Venn diagram we could create regarding this topic. And both of you gentlemen have strong backgrounds in engineering and in essentially physics and in understanding the flow of electrons, right? So you mentioned, John, the Emerging Technology Center here at the SCI. And today we're going to be focused, but not exclusively, on sort of the differentiation between quantum computing and classical or classic advanced computing. Now, there are important distinctions to understand there. And I was wondering if Jason, you could start us off by explaining at a high level what quantum computing is and how it differs from classical computing. And then maybe, and I know this is a bit nuanced, what do we mean by advanced classical computing?
Oh, okay. Well, how about maybe we can start with what's advanced classical? Well, I mean, John will say more about that, but let's say advanced classical is like whatever are the state-of-the-art techniques which are trying to overcome standard commodity computing, let's say. For quantum computing, how is it different than classical? Well, there are many similarities, but there are also some key differences. It might take too much time to get into these, but the key differences are the fundamental components that make up quantum computers. These are qubits instead of classical bits or C-bits. That's where the differences start. It would take some more time to explain the rest, but it is a new form of computing. It's distinctly different than classical computing, either commodity classical or advanced classical techniques. And what's also interesting is that we're going to need a lot of classical high-performance computing to make quantum computing realized. They're going to be married together intimately. So how about that? Is that a good start?
Fantastic, Jason. Yeah, I know I asked sort of a difficult to answer question, or at least difficult to answer concisely. So John, do you want to take up the other part of that question?
Yeah, I'm happy to. So when we talk about advanced computing, you can also call it sort of high performance computing is sort of a synonym. And really, like Jason alluded to, it references making use of sort of the cutting edge in computer hardware and computer software. And the sort of, I'll talk about this a little bit more later, I think, but the sort of the level of detail that spans, from just writing a Python program and then running it on your CPU, the difference between that and then writing a code that would execute on a supercomputer, for example, using sort of new hardware, whether it's GPU or FPGAs, those kinds of things. Sort of the amount of detail that that differentiates those two tasks is enormous. I mean, and there is just a ton of information. And so we sort of like to say that we're, towards the advanced end of that spectrum in the sense of our knowledge and what we need to do in order to get the computing resources to do what we want.
Thanks, John.
Mm-hmm.
I could add maybe one more thing. You can maybe wrap up what John's describing as kind of like cosynthesis, where the software and hardware are designed, created together. What's interesting about quantum is that we're already in a cosynthesis situation, where I think as quantum goes on, you're going to need essentially to specify some high-level application, and then to take it down to the quantum hardware is actually very challenging in much the same way it is with classical.
So that's really interesting, Jason. So what we're saying is there's essentially a convergence or evolution. It's not a replacement scenario, essentially, right? That which is, I think, really important to understand. But I realize now I was remiss in not asking a very kind of fundamental question, which is, why quantum? What is the promise of quantum? So, John, you have some thoughts about that? Why do we pursue quantum as a line of research in computer science?
So I actually don't do presently any work in quantum. So I want to defer that one to Jason.
So I would say that we're looking at quantum for similar reasons why we're looking at other forms of advanced computing to try and overcome the so-called Moore's law is dead issue. Then the question is, what is quantum good for? And we have some good ideas about what those things are now, but we need to discover what they are going forward, because establishing the complexity theoretic evidence is very challenging. So what we're going to have to do is combine this complexity theoretic guidance with actual benchmarks, actually building machines and running tests and evaluations.
Thanks, Jason. And John, apologies for sort of that maybe incorrect redirection, but maybe let me reframe what I was asking. So what are the topics then in advanced classical computing that you are working on that you see as being complementary of the efforts that Jason's leading in quantum?
So, well, like Jason said, a classical computer is going to be involved in execution of quantum computers. I was actually just having a talk today with one of our senior scientists, and he said, what I have to understand, so quantum, you have this collection of quantum processors. They're in some sort of array, and you write a quantum program, and what that really does is it issues a series of, and so I'm getting a little bit out of my element. Jason will rein me in if I'm wrong, but it issues a series of microwave pulses, which is how the qubits are sort of transformed. So he's like, well, what happens if I have I issue a microwave pulse, and then this other qubit is not in a proper state? And so we discussed about, I don't know what runtimes look like, runtime libraries and things look like for quantum computers. I don't even know if they exist, but that's very much sort of a classical kind of thing. Is the quantum computer going to be synchronous? That is, you can only issue new microwave pulses once you're sure that it's in some sort of steady state. So that's very much sort of a classical thing. Runtime libraries, runtime scheduling of operations, and that sort of thing.
Thanks, John. So it sounds like then classical computing, to state the obvious, is the template, and then the question is, how does that template or that model of operation and architecture then evolve for quantum? And I think this conversation illustrates a really important point, which is in the ETC at the SCI, we are engaged in work on the very kind of tip of the field, right? We're working on cutting edge technologies and concepts, this being one of them. So a question about the sort of folks that work in this field. So certainly you gentlemen did a great job of explaining kind of how you got into the field, but I know that we're looking for other folks to join us in this pursuit, right? We're looking to recruit. I was wondering, Jason, if you could maybe start us off on the background we're looking for. What are the skills or the education path that we're seeking in the candidates that the SCI will be soliciting for your open positions?
Oh, yes. So I think overall, we're talking about quantum and advanced computing. I think overall we're looking for people who have experience in hopefully multiple forms of advanced computing, if you can get it, and the ability to understand multiple forms going forward. Because I think if we're learning a lesson here, it's that we're having lots of new compute platforms, both classical, quantum, and otherwise, emerge. And so I think, broadly speaking, we're looking for people who have general advanced computing experience. That's hard to get, but that's what we would like. And then furthermore, for quantum, there are particular, domain-specific aspects of quantum physics and quantum computing that we would like to find as well. But also looking for people who are able to train and upskill. And we've done a lot of experience with this in internal SEI with the people here who are working on quantum-related projects, and also with SAMU.
So I guess like all new fields or emerging fields, if you attract folks that have a strong intellectual curiosity, that have good critical thinking skills, you can then bring them into the discipline and domain, right? That's what I'm hearing. And John, do you need a PhD to do this work? Is that essential?
No, it's not.
Okay.
We have some PhDs, but we also have sort of we have bachelor's level folks that are doing what I'm calling advanced computing, and they're making excellent contributions. Like Jason said, the primary requirement is that you're curious. Well, you're interested in expanding your skills in this area, and you're motivated to do so. So I'm gonna, if I could say a few more words, sort of about so you might be able to tell that Jason and I are a little bit separate, but we're sort of in the same ballpark. I work on different programs than Jason has. I haven't yet worked on any of his quantum stuff. Maybe there will be a day when we do that or not, or when I do that, but we'll see, I guess.
Yeah, and sorry if I've been a bit reductive sort of in describing this as sort of one thing. I understand and thank you for unpacking, explaining the important distinctions between these two related but unique fields. Yeah,
so I'll speak sort of briefly to what the projects that I work on, which are largely in support of DARPA Microtechnology Systems Office. We're on a couple different programs. And what I like to say is that we focus on everything from algorithms to assembler. So we need to know how algorithms work, machine learning, graph analytics or graph machine learning, high-level programming languages, Python, C, C++, compiler technologies, abstract syntax trees, intermediate representations, interpreters, runtime libraries, low-level language concepts such as assembly, and then like cycle level performance considerations on hardware of memory hierarchies and compute units and that sort of thing. So that's a whole lot of stuff. And we don't, to find someone with expertise across that entire stack that's the unicorn, I think. And so I would say that even our senior scientists, none of us have what I would call deep expertise for every single one of those things. We have, expertise at a couple of them, and then certainly knowledge across the spectrum. So, so with that characterization, I'll just sort of restate that, we're interested in, people who find that kind of thing interesting and have maybe demonstrated some, expertise in at least one of those things or some sort of, decent competence. And then an interest to sort of broaden their perspectives and learn more about any of that. And later, if you want, we can talk about like the specific DARPA program activities, but for now, I'll leave it there.
Well, thanks, John. And Jason, just to build on the idea of the customers or partners we have in these two fields. So John mentioned DARPA. Can you maybe elaborate on other customers or partners that we have here at the SEI in these fields?
Yeah, so, maybe I can comment on who we collaborate with.
Sure.
So our collaborations include industry partners. So we're part of the IBM Q network. Okay. So we get access to a lot of their resources, including their devices, which are very useful for doing testing and development and so forth. We collaborate with other researchers at other companies and try to stay very connected to the developments in industry, because we're seeing a lot of them and very rapidly, especially in the past 6 months. We have like official detailed, blueprints of the different companies and their, plans to build their computers and so forth. And then we also collaborate with different labs at AFRL. I think that's a pretty good description. There's more details on our website, actually. I think at SEI, there's an official quantum page that has a lot more details.
Yeah, thanks, Jason. I was going to mention that if folks are interested, and I certainly hope they are, if they're interested in just the subjects or in joining us, if you go to the SEI homepage and then to ETC, and there is, as you said, there's a landing page for quantum and quite a bit there. And
I'm sorry, I should also mention, we also collaborate with several groups on campus, Carnegie Mellon, including Franz Cronketti's group in the ECE department. We're looking to expand the collaborations there if we can. We also collaborate with the Pittsburgh Supercomputing Center, who provide us with classical computing allocations, which classical HPC is important both to sort of create the quantum computers and control them. It's also very important to provide as the juxtaposition or the comparison to whatever you're trying to do quantumly that you can do classically, including things like simulating quantum computers and running modeling and simulation, and also benchmarks on state-of-the-art classical devices.
Thanks, Jason. Have a better understanding now of the two disciplines, the two fields, the folks that we interact with and collaborate with, the kind of people we're looking to attract. And as you mentioned, Jason, there are things that the SEI has published and things we've said about quantum and classical advanced computing available. Just a question about where we're headed. So you mentioned that 6 months is in your field in quantum computing is enough time to see something significant change potentially, right? Which is not the case in all fields. So with that said, it feels like this is truly, to use a cliche, right? This is truly sort of a ground floor or, first wave opportunity to work on these technologies. Can you comment on that, Jason?
I think you have it right. It's certainly, there's a bunch of different ways you can measure the growth, like the amount of increase in funding and publications and these kind of things. So I certainly think, and there's a ground floor aspect to it, like you mentioned. I think you're going to see like prolonged investment over the next 5 to 10 years from different organizations and so forth. Meaning I think there's work, to be done and research to be done in this field, a lot of it, and it's the ground floor, like you mentioned. Yeah.
So please, Jason, I didn't mean to speak over you.
I'm trying to think of, can you reiterate what your statement was? Because I don't know if I addressed it all.
Yeah, I believe you did, Jason, but please, the statement was that because the field is so nascent, it's really a unique opportunity, right? You are seeing this from the ground up, essentially. Right?
Yeah, absolutely. Like 1950s classical computing, something like that.
I was thinking about that. This is Southern California in the 50s, and we're playing with semiconductors for the first time, right? And with circuitry, right? So John, just a question then about where classical advanced computing is heading, right? So at some point, do you see that it is eclipsed by quantum, and how far in the future is that, if so?
So I think there's unanimous consent that it's not an either or. I think there's unanimous consent that both there will be a role for both. And at the very least, the classical computer is required to drive the quantum machines. But then also, I think Jason just alluded to, there are algorithms that don't really make sense at the present time for quantum. So in terms of advanced computing more generally, somebody said a couple of years ago, guy's name I think was Carl Freund, the AI hardware is in a Cambrian explosion. So we're actually witnessing right now, and over the last 5 years and the next 5 to 10 years, a rapid growth in application-specific integrated circuits. So and so you might know some of these names like Cerebrus or Grok or SambaNova. I guess I shouldn't say some names if I'm not going to say all the names, but these are AIs, Google TPUs. These are AI specific pieces of hardware that are being developed because of the opportunities that are present right now. And so it's a really exciting time to sort of be in advanced computing.
Well, thanks, John. I work for the CERT division of the SCI, so my focus is security. And we tend to focus on defending against challenges in quantum computing or defending the quantum devices themselves or quantum computers. But I mean, this field is far more expansive than I know, right? So when do we think, and maybe this is a question for Jason, when do we think that the average consumer will see a viable quantum computer in their life?
Oh, okay. So we have to define what the average consumer is and so forth, right? How about this? How about we dial it back to when will we see a mass use within data analysis or something?
Okay, that's a fair starting point, sure.
Like how we call GPU,
Sure.
I don't know if it'll ever have a market share like GPUs have now, or maybe GPUs are going to lose a lot of their market share given what John mentioned. But let's say, I think this time frame is something like the next 5 to 10 years.
5 to 10 years, okay.
Yeah, I think what you're seeing now in the early adoption phase are there's people doing that, and they're trying to get quantum ready, as they say. As the hardware improves, they want to be ready to capitalize. But I think it also depends on what the application is in the field, the domain. So I think other domains will have application advantage sooner. I think that's reasonable. So yeah, I think reasonable is something like 5 to 10 years.
5 to 10 years. So Jason, just another question in my mind. So if you could do a little quantum myth busting, what is a common misconception about quantum that we should explain to our audiences is just fundamentally untrue, if there is such a thing?
Oh, okay. Well, one would be whether or not you'll use them to do everything that classical computing does, and that's very far from the truth. It'll be some small fraction of what we, and it'll be things that we want to do that are game changing, transformative applications that you can't do with classical, at least right now. And then the other thing is this notion that quantum computers are able to just try all these possible solutions to given problems, and it does this in parallel in some way. And that's not true either. That's not really what they're doing. Scott Aronson's blog is a great blog to just debunk quantum myths in general. And he has this one myth I just mentioned as his banner. So go to Scott Aronson, Google Scott Aronson blog and
Scott Aronson. Okay, great. I will. Yeah. So John, on the classical advanced computing side, is there something you'd want to impart to the audience regarding what's maybe a misconception or a sort of a falsehood about the state of the practice or state of the art?
Nothing's coming to mind. I mean, the one thing that sort of people should be aware of, and it's not a misconception, is sort of the edge, the growth at the edge, and by the edge we mean what your telephone in your hand, that sort of thing. And advanced computing is coming to those devices. Things like right now, if you have you take a picture of your kitty cat, it gets sent up to the data center where the training is done, and then then the model comes back to your phone, and that's how it works. But more and more, the actual compute is going to be moved out to edge devices, and that's a real strong growth area in the future.
So that's a really interesting example in that the mobile phone is ubiquitous. We're all carrying this fairly powerful computing device in our pocket, and then really leveraging that compute power on the edge. I think it also, in your description, John, it speaks to something else, which is these changes might be profound, but largely and maybe ideally seamless and transparent to the user, right? So We have the opportunity working for the SEI to explore the concepts and the tech behind these things, but most folks just think in terms of upgrades to their lives and capability or function, right? So I would just put the cell that if you're interested in not only sort of where we're headed from a technology perspective, but ensuring that you can build things of significance for the future, the SEI and specifically working with these gentlemen, the ETC, is a great place to be.
I agree.
So one last question as we close on the end of our time, and I'll start with you, Jason. One piece of advice for those interested in quantum, something they can do this weekend to get smarter. You mentioned a blog. There's the SEI resources. Where would you start if you're kind of a novice in this topic and want to learn more?
So yeah, I guess it does depend on where you are as a novice. So I would like to give more targeted advice, but if I could just give only, like, you're going to go this weekend and you're going to do some activity or something that gets you into quantum. Well, there's a lot of nice resources in terms of like kizkit.org is good. Like IBM has a whole entire like quantum Kizkit package with a book, and you can get access to notebooks, and you can actually go program an actual quantum computer in the cloud. You can draw quantum circuits and all this. There's other packages and people that have simulators that are even more easy to access than IBM's. Maybe I could put a list, because quite frankly, I can't really isolate down on one. It depends a lot on what kind of novice and what they would how they would prefer to learn. Do they want YouTube lectures? Do they want notebooks to interact with? But there's tons of resources.
There's lots of stuff out there, is what you're saying.
Yeah.
Okay. And John, over to you. So in the advanced classical computing space, let's say you're a computer scientist and you're interested in, and well, certainly if you're watching, you're interested in these topics, but let's say you're interested in expanding your skills and knowledge. What would you point to in your domain as a next step to sort of learn more?
So I was gonna pivot just a little bit. I was gonna say, since people are more and more developing like AI and ML algorithms in these frameworks like PyTorch and TensorFlow and these kinds of things, for a lot of people that's sort of the end. They're probably training their algorithms on GPUs locally and in the cloud and whatever. And for a lot of people, that's sort of that's good enough. That's all they want to do. They just want to get to their end. Their model that they can make their predictions with. So if you're interested in sort of advanced computing aspects of that, what I would say a good test would be to try to go find like the CUDA code that's responsible for implementing those algorithms on the GPU. So it's all out there. Well, yeah, I guess I can't say 100%, but certainly PyTorch and these things, those are all open source. And in principle, you should be able to drill down from the GitHub, to find the kind of code that we are, that really draws our attention. So, trace it all the way down to sort of the detailed code you have to write in order to make maximal use of these advanced computing resources.
Well, excellent. I'm sorry, Jason, go ahead.
And it turns out that actually I would suggest the same thing for quantum, the ability to dig into all this software and code down to the very lowest levels and reasonably understand what's going on at every level. Because now for the near future, that's what developers are going to have to do. As time goes on, we'll see emergence of, separation of the stack and concerns.
Thanks, Jason. So what I'm hearing from both John and Jason is that if you have a desire to learn more about this, you can do it essentially at no cost other than your own time. It's not like you have to enroll in a PhD program to learn these things, and that true innovation and understanding are kind of not beyond anybody, right? Anyone with an interest can learn something about this. So, well, John and Jason, I certainly appreciate your time this afternoon. And if folks are interested in a role here at the SEI working in advanced classical computing or quantum, certainly look at our open positions on the SEI website. So thanks again, and look forward to future sessions where you can update us on the progress you've made and the exciting new things we're doing with both advanced classical computing and quantum.
My pleasure. Thanks, Matt.
Yeah, thank you.